I'm going to talk to you about two projects, two EU-funded projects. The first one is this project called Project Natura. It's an EU-funded integrated project. It's a Framework 6 project which comes to an end at the end of this month. It was a 4-year project. It had about 30 partners and a budget of about €24 million. The role of the University of Greenwich in this project was to look at the blended wing-body aircraft that you see here and undertake evacuation and fire analysis of this aircraft to come up with a design that was considered to be safe from an evacuation point of view. So that's what I'm going to be talking about during this presentation. I'm going to be talking about some computer evacuation modelling we did, some full-scale experimentation we did to back up the modelling, and then if I get time to talk about some of the fire modelling and how we combine the fire and evacuation modelling together. So, why do we want bigger aircraft? Well, the aviation industry's drive for increased efficiency has led to the development of larger and larger aircraft. Today we see the Airbus A380 as being the largest passenger aircraft that's currently flying. It has a capacity of up to about almost 600 passengers in a single class configuration, and this is considered to be, it's still considered to be a conventional aircraft. It's simply a twin-aisle aircraft with 2 decks, similar to other twin-aisle aircraft and similar to the 747. To achieve even greater efficiency and passenger capacities, the aviation industry is turning to less conventional designs. This is about as far as you're going to get with a conventional tube-style aircraft. So we're looking at less conventional designs. This is not a real aircraft, but this gives you an idea of the type of space that you require in these aircraft to get bigger and bigger capacities. In fact, when we look through aviation history, there's been quite an interest in these blended wing-bodied aircraft. In fact, it dates back to the 1930s with early designs for these types of aircraft. The first was a German design from the 1930s, and then Italian designs, Russian designs, US designs, European designs, and so on. So what we're going to be talking about is this type of aircraft, this blended wing-body aircraft. The work on this actually started in a Framework 5 project called Vela, and it's continued into this Framework 6 project. Now, the blended wing-body represents a significant departure from tube-style aircraft, and so there are a number of challenging questions that need to be addressed in order to consider this sort of design acceptable from a safety point of view. Passenger safety is probably one of the most important aspects of this design. Believe it or not, most of the aerodynamical questions about this sort of aircraft are solved. And so one of the big challenges that remain are questions about passenger safety. And there are two fundamental questions. Firstly, how long will it take to evacuate a BWB aircraft? And how will the evacuation efficiency be affected by the passenger load, the seating arrangement, the nature of the longitudinal cabin partitions, the cabin aisles, the number of staff, the number of exits, the type of exits, the location of the staff, the types of cabin procedures, emergency procedures, and so on. All of these things will have a huge impact on evacuation of this type of aircraft. And then we have the other set of questions. How much time is available to safely evacuate a BWB aircraft subject to a post-crash fire? The aviation industry uses the standard 90-second certification requirement as a benchmark test for evacuation. The 90 seconds coming from a flashover requirement. Basically, if you're in the aircraft and there's a fire, after 90 seconds the plane is set to have flashed over, and so if you're in the aircraft, you're dead. So you have to be able to get off before 90 seconds because of this flashover effect. So for a blended wing body, it's not a tube, it's a very different interior shape, and so when will flashover occur in these types of structures? And what type of fire hazards are going to drive the non-survivable conditions on board these type of aircraft? And I guess the ultimate question we're asking here is the 90-second certification test that we use for tube aircraft, is it really relevant for this type of aircraft? So Project Natura we looked at a particular basic design and layout of the aircraft. And what I'm showing you here is the so-called FW1-1-1 configuration. We actually looked at about 6 or 7 different configurations. But this is one of the base configurations that we use for comparison purposes. And what you see here is a seating arrangement, a 3-class seating arrangement for a single class configuration. So this is all economy, all coach class, for 1,020 passengers. We also have to have 25 cabin crew on board, and the reason we need 25 cabin crew is we need 1 at each of the exits on board the aircraft, and this aircraft will have 20 standard Type A exits, the sort of exits you get on the 747, plus there will be 5 additional crew in the body of the aircraft to try and help move the passengers. We have 8 longitudinal aisles, so unlike on the 747 where you've got 2 aisles, we have 8 aisles here, and we have a number of very long cross aisles as well. So that's the basic layout. Where each of these blue tabs are, this is an exit on the aircraft. So you have exits all around the periphery of the aircraft. Okay, so we did a number